back to our example, which we started discussing in the previous class. This class may be a little bit shorter. We'll see where we finished. We'll finish. So we started discussing a linear triatomic molecule, right? You remember the system is like this. We have three masses, two identical masses on both sides of the system, and the central mass is M capital, right? And springs connecting these masses are identical. So we have two springs, right? So we introduce so far the most convenient coordinates 8 etas, right, which defines position of particles relative to the points of equilibrium. So then we introduce potential energy matrix, real, symmetric, kinetic energy matrix, real, symmetric, right? Then we found eigenvalues, three frequencies, omega 1, omega 2, and omega 3. And then we started looking at each of these, at each of the modes, because this is the mode of the frequency of the first normal mode, frequency of the second normal mode, and frequency of the third normal mode. So we finished discussing the first normal mode, right? We found eigenvector using Eigenvector Equation, and we also normalize it, right? And and then we sort of sketched this mode, this first normal mode. In this case, all particles are displaced in the same direction by the same amount, right? So as a result, distances between these masses are not conserved, but stays the same, right? Only in this mode, right? So you need to apply certain initial conditions in order to sort of trigger only this mode. Actually, I think I watched the video, right? In MIT, there is a group, sort of like the group which sets up experimental demonstrations, right? And actually, a few years ago, we had a student here, a graduate student, who worked in that group. So, but anyway, so that group demonstrated some of the modes for a system similar to this. Of course, if you create initial conditions properly, you can trigger only that particular mode where the particles oscillate either out of phase or in phase, and so on and so forth, right? There are some interesting videos on YouTube. Right, so then, after this, we started looking at the second normal mode. We started working with this frequency, and after applying Eigenvector Equation, and after normalization, we ended up with this eigenvector, right? Which tells, normalized, right? So which tells us what? Amplitude of the first particle in the second normal mode, amplitude of the second particle in the second normal mode, and amplitude of the third particle in the second normal mode, right? Amplitude of that particle. So now let's just sketch this mode using this simple picture, and then we'll move to the last mode. All right, so in this mode, the central mass is stationary, right? It doesn't move, right? So it doesn't move, and the outer masses move out of phase, right? Okay, let me draw here, there. And if, for example, this mass moves this way, let's say, it is eta 1, this will be moving in the opposite direction, so this will be eta 3. Or if this moves in this direction, of course, this will move in the opposite direction with the same amplitude, right? So pretty much they move in such a way that the center of mass stays at the same place. And again, using two fists and the head, it's sort of basically like this, right? All the time they move. It's sort of like exercising, right? Exercising some of your muscles. All right. So now let me frame this mode, right? And now the last one. Okay, I will probably move up here, right? And rewrite that frequency, omega 3 equals square root of k over m, or 1 plus 2m small over m capital, right? And then we need to shove it as usual in Eigenvector Equation, all right, which is V minus omega squared t, and eigenvector, this is now number 3, equals 0. And of course, also I mentioned in the previous class, so what is good about this system, there is no degeneracy. All frequencies are different, so it means that automatically all our eigenvectors are orthogonal to each other. So this is orthogonal to that, and this will be orthogonal to the one which we will create in a few minutes, right? Okay, so I'm not going to write everything because the procedure is well known and somewhat tedious and lengthy. So I will just write down the final form of the matrix, this matrix, right? When you subtract V minus omega squared t. Actually, here I should put subscript t. Right, so if you do that, you will get with minus 2m small over m capital K, then minus k 0, then minus k m capital over m small. Here, just a little bit of massaging. Right. You will end up with this. It's very simple, and so I decided to skip. So minus k and 0 minus k and minus k 2m over m capital, the same like that one. And the eigenvector. Okay, so now this is the amplitude of the first particle in the third mode, then amplitude of the second particle in the third mode, and amplitude of the third particle in the third mode. Right, and it must be equal to 0. Again, system is underdetermined because we know the determinant of the system equals to 0. We demanded that. So it means that out of these 3 equations, which we can write, only 2 will be linearly independent. So only 2 useful equations, right? And now it means that we can, so 2 equations and 3 unknowns. That's what I meant by underdetermined system. Which equations are used? The first one and the last one, the easiest one, right? So I will use this one and this one because the middle one have all 3 terms, just messier, right? But we know one of the equations can be dropped, right? Because it's a linear combination of the rest. So if you write that equation, those equations I'm not going to do, but anyway, I emphasize that I'm going to use this and that. You will end up with what? That A 3 must be equal to A13. Right. It's very trivial. And A23 equals to minus 2m small over m capital and A sub 3. Right? So now if we take, for example, A13 as 1, then we can write in terms of A13 the rest. But since still we have a freedom, right? So we have underdetermined system, we can introduce normalization factor, right? And with normalization factor, it will be equal alpha 1 minus 2m small over m capital and 1. So with normalization factor, right? Yeah. And so after, again, I'm applying normalization, so which is A3 transposed T A3 must be equal to 1. So after applying this normalization procedure, which is again straightforward, right, you will end up with vector. Okay, you know what? It's too long. Let me write first normalization factor, and then I will write vector underneath. So normalization factor will be equal 1 over square root, because I don't have enough space. I thought I would be able to fit eigenvector. So square root of 2m, 1 plus 2m small over m capital, right? So normalization factor, and now the vector. Yeah, logically it's better to write here. First I thought about there. So A3 will be equal 1 over square root of 2m1 plus 2m small over m capital and 1 minus 2m small over m capital and 1. So that's the last eigenvector. Okay, so I need to frame it. Yeah, and so now again, let's sketch this mode. Probably I will sketch it over here. So now we can see that outer masses move in phase, in unison, right? And the outer mass is out of phase, but with different amplitude. If mass m capital is larger than 2m, the total mass of the outer masses, then amplitude of this will be smaller than 1, so it will be displaced with smaller amplitude. Of course, if 2m small larger than m capital, of course, this mass will be displaced with, is displaced with larger amplitude, right? Okay, so let me draw something about that. So bigger mass, then this, then spring. And so if these two guys are displaced to the right, so this is eta 3 and this is eta 1, then the outer mass will be displaced in the opposite direction with amplitude, of course, eta 2, with amplitude eta 2. Or in the opposite, so if we have eta 1 this way, eta 3 this way, then eta 2 will be in the opposite direction, right? Again, with the goal to keep the center of mass point stationary, so the center of mass doesn't get displaced. So it's like this, right? Something like this, right? Of course, as I told you, there is a researcher at STL. He does it much better, much funnier, right? I still remember, again, as I told you, STL uses CO2 lasers a lot. So for every new students, right, he had to explain how it all works, right? A little bit of physics, right? And he uses all the time, right? All these modes. Right. So probably you know what. Let me mention about the center of mass stays system. The center of mass of the system fixed, right? So let me emphasize on that. So the center of mass of this system in this particular mode, of course, in the system, which we wrote, is fixed. Okay, let me write is fixed. So it doesn't move. Right. So now after this, okay, so we have all ingredients, all pieces in order to start writing down general solution. Right. So all preliminary steps are done. So now, okay, so first general solution of the whole system, and then normal coordinates. Okay, so now general solution. Right. So eta 1, eta 2, eta 3 equals. So which constants I use? Okay, F. Okay. So it's a linear combination of all these modes. So this is our first mode. eigenvector. So it will be f1, constant of integration, then this normalization factor, 2m small plus m capital, and eigenvector 1, 1, 1, and time dependence cosine omega 1t plus delta 1, and of course omega 1 is 0, right? So let me dump this, right? So first part of general solution now, second, so f2 and divided by normalization factor is 2m, and eigenvector, so it will be 1, 0, and 1, right? And time dependence, oops, cosine of, okay, you know what? Because even omega 3 will be kind of complicated, so I will just write omega 2, omega 3, right? Just to save space. So omega 2t plus delta 2, and then plus f3 divided by square root of, where's my normalization factor? Okay, I have to write normalization factor. It's 2m 1 plus 2m small over m capital, close square root, and 1 minus 2m small over m capital. This ratio of 2m small over m capital almost everywhere in the third mode. And time dependence, cosine omega 3t plus delta 3. So that's the general solution of the system, right? And of course, as usual, right, so if you're interested in a general solution of the first particle, this one, grab the first line, so pretty much eta 1 equals f1 divided by this times that times cosine. Then f2 times that, okay, with the normalization factor, and times that. And then the first element in the last part of general solution, right? And then eta 2 and eta 3. Right? Okay, I'm not going to do it now. Now, of course, next logical step, yeah, problem is solved. You have general solution. You can just apply initial conditions, find those constants, and you should be able to describe any possible oscillations of this system, right? But now we know that there are normal coordinates where the solution will be easier, right, and so on and so forth, right? So let's find those normal coordinates. And in order to start searching for normal coordinates, of course, we need to construct a model matrix. Remember that A, right? And since these normalization factors are kind of not ugly, but kind of too much to write. So let me sort of label or denote. All right, so let me call this 1 over this, right, as A. So it's a 1 over that. Not just, okay, maybe I can write over here just 1, right? 1 over that square root as A, because otherwise, once or twice I used all those square roots, and then it's so tedious, right? Then this, let me call it as B, and this construction as C. All right, okay, and now I will have to write less. I can construct the model matrix. So now model matrix, matrix A. So, and you remember how A is constructed. So you take the first normal mode, position it as the first column, then the second, did I say normal mode? Eigenvector, the first eigenvector, then the second eigenvector. All right, then the last eigenvector, and position them as columns. Okay, so the first A1, it will be this constant A, A. So it will be A. So that's what I can get as a first column. So it's this A times all those ones. Then A2, it will be B times that. So it will be B0 minus B. And the last one, A3, so it will be C times that column. So it will be C minus 2m small over m capital C, and also, hold it, C. Yeah, they oscillate in phase. Good. Sometimes I doubt myself, right? Okay, so that's the model matrix. And now model matrix makes all these transformations. You remember that those congruence transformations are done through the model matrix, right? If you want to move from the old coordinates to the new coordinates, which are normal coordinates, again, it's all done through the model matrix. So it's the biggest troublemaker, right? So making all these transformations, model matrix. Okay, so now you remember how we constructed the normal coordinates. First, in order to move to the old one, eta equals A times xi, right? Yeah. So that's how we can move from normal coordinates to the regular coordinates, the most convenient coordinates in terms of description of the system. Because xi, yeah, the xi is the most convenient in terms of solving the problem, right? If you have a system written in xi, solution is basically the easiest possible. But in terms of description of the system, at the end of the day, when you want to see how all particles move, of course, you need to go back to etas, because they define position of particles, right? Okay, so that's if you want to go to etas from xi, but that's not what we want. In the opposite direction, we showed in the previous class, you need to multiply these matrices. So first, A transposed T eta, so multiply. And again, you remember, this is column, and of course, those are matrices, right? So that's what, of course, we need in order to introduce normal coordinates. So now we have all the pieces. T is here, model matrix is there, and eta, yeah, we know. So of course, you will have to go through this mass of massaging these three matrices. So we need to transpose this, right? This matrix A. So it means that AAA will be as the first row, AAA. AAA. It reminds me, you know what that sound, AAA, sounds like KKK. Right. Watch a few documentaries recently, so. All right. So B0 minus B, B0 minus B. All right. And then C minus 2m over m capital C and C. Right. So that's transposed A. Don't forget to transpose. I remember once, no, a few times I made that mistake. All right, then kinetic energy matrix. It's trivial. M0, 0, 0, M capital, 0, 0, 0, M. And then column of the displacements. So it's not that difficult to go through this mass. I'm not going to do it. Just a little bit lengthy. So I will just grab my notes and write the answer. All right. And of course, A's, you see what is A, what is B, and so on, right? So after, I don't know, 5 minutes of simple calculations, you will end up. Psi1, Again, so this is, you know what, I should have written probably this as a column. You know what, yeah, it's not a good, let me fix it. Psi1, Psi2, Psi3. Okay, so this is better. This is way better. Although what I wrote before was also not wrong. I could say that was the column, right? But it's better to show it explicitly. So again, if you go through this, you will end up, okay, I will just grab my notes and rewrite the linear combination of these etas, which we need to construct in order to get the first normal coordinate, psi1. So it will be m small times eta1 plus m capital times eta2 and plus m small times eta3. So that's the linear combination of old coordinates, the most convenient in terms of physical description of the system, to sites which are the most convenient from the mathematical point of view. All right, so then the second one, side 2. Okay, this is the easiest one. It will be square root of m over 2 and eta1 minus eta3. You see, immediately I went back to our constants of the system, m capital, m small, and so on. So I dumped these constants. Okay, and the last one, psi3 equals, okay, ugly constant. Actually, m is not part of the square root, so it will be m divided by square root of 2m and 1 plus 2m small. Okay, it's m small divided by m capital, and linear combination of those etas. So eta1 minus 2 eta2 plus eta3. And let's just quickly check one of these coordinates. You remember what's the major feature of normal coordinates? Each of these normal coordinates are supposed to oscillate only with one frequency of the normal modes, right? Either omega 1, either omega 2, or omega 3. Right, and out of these three coordinates, of course, the easiest one, the second one, let's just quickly check the second one. Are we going to get oscillation of this coordinate only with one of these frequencies, right? And again, every time I try to control myself to say correctly, these coordinates oscillate, not the particle, because you remember these xi's, they can define positions of any points in the system, right? And that point doesn't have to represent the position of the particle. Etas, yeah, etas represent positions of particles. Xi's, who knows, right? It depends on the system, right? So let's look at the second one. And so we have eta1 minus eta3 with that factor. So where is my eta1? Here, eta1, it's the first line in this solution. Eta3, of course, the last line. Okay, so let's look. If we subtract eta1 minus eta3, let's look at the first mode. If you, okay, factor, of course, the same for all these etas, right? This and that part is exactly the same. So we need to look at the eigenvector. So if you subtract eta1, this one, minus this one, of course, the amplitude will be 0. So you'll get 0 amplitude of this mode. So omega 1 is not part of psi2. So this psi2 is not going to oscillate with the frequency omega 1. Now, let's look at the last one. Again, this factor and that time dependence exactly the same for all these etas. So it means that we need to look at this column again. So we're subtracting eta1 minus eta3. So 1 minus 1, of course, gives you 0 amplitude of this a normal coordinate. So it means that 0 amplitude with this frequency, it means that it doesn't Xi2 doesn't oscillate with frequency omega 3. Great. So it doesn't oscillate with this frequency, that frequency. Now let's just quickly check, just to be safe, the second normal mode. Okay, we're subtracting. So if you take this minus that, so it's a 1 minus minus 1, it's a 1 plus 1, 2. You'll get amplitude of 2. And then this factor. So we have 2 in the numerator and 2 downstairs. So you will get over here square root of 2 over m. You will have square root of 2 over m. Now let's see what we have in front of this. There we had 2 over m. Here we have a square root of m over 2. You will get just 1, right? 1, and this, okay, factor of 2, of course. So it will be f2 times that time dependence. That's what we wanted. That's what we are originally planning to get. So I'm not going to write it. I will just write, so it's a actually at the end it is equal to that constant of integration f2 and times time dependence cosine omega 2t plus delta 2, right? Yeah. Oh no, instead of check mark, let me put a happy face, right? Yeah, that's what we wanted. And of course, analyzing Xi1 and Xi3 more complicated. No, so we're not going to do it. All right. So these are normal coordinates, of course. I need to write that down. So these are normal coordinates, of course. Normal. That's how we can get them if you solve the system and found etas. Yeah. And of course, you can also, if you want to convince yourself that the Lagrangian will have only diagonal form, only quadratic terms, it will become, of course, significantly messier because we had Lagrangian at the very beginning in terms of etas. So you will need to get etas in terms of xi's because now you have xi's, right? It's a real mess. It will be a real mess, right? But we proved mathematically that a Lagrangian is going to be diagonal also, right? There wouldn't be any coupling terms, right? Only quadratic terms, right? So we're not going to show that. Okay. Anyway, I just was planning to get normal coordinates and stop at this point. Stop at this point. Okay, so that's the example. Again, it's straightforward but very tedious, right? On the verge with boring, right? Then I usually discuss system of what? Two oscillators weakly coupled. Two weakly coupled oscillators, right? But I doubt that we will be able to finish it. It's like, yeah, maybe half an hour of work, right? So I will skip it, right? I will skip it, right? And now let's talk about the tricks which can be used, right? So it's great when the system is written in terms of normal coordinates, right? But it's almost next to impossible to see how we can construct these normal coordinates from the very beginning when you're just in front of the system and you don't know anything about the system, okay, in terms of solutions, right? So from the very beginning, it's difficult to see normal coordinates, except for when the system is reasonably nice. We will discuss it now. Sometimes you can kind of not guess, but deduce, right? Somehow you can construct those normal coordinates, and as a result, solution will be somewhat simpler, right? So that's what I want to discuss now. So that sometimes we can see normal coordinates from the very beginning. So let me pick some reasonably simple system, similar to this, right? And first I will get through the fail-proof solution. But again, just major points, key points, without getting through all this mess, right? And then we will look how we can get normal coordinates without getting this tedious fail-proof solutions, fail-proof approach, right? Okay, so now let me erase this. Yeah, I don't need this. So let me write something like this. This is too long. I will just write trick method. Why not? Probably a tricky method. No. Let me write. Oh, approach or method. Right, something like that. Okay, so let's assume that we have this system first. A wall, right? Then there is a spring. Then there is a mass. Then, okay, another spring. Then another mass. And another spring. And the wall on that side. Let's assume the system is reasonably nice, the same masses. So let's say this has a mass m small, k, k, and k. Okay, now it sounds like KKK, right? Right. I need to watch less documentaries, right? Okay, so typical displacements, eta 1 and eta 2. All right. And fail-proof approach. First, we will apply fail-proof approach. Right. So first, fail-proof approach. And then actually, like shortcuts or trick which can be applied, a trick which can be applied. But first, classical. So first, of course, we need to write down the Lagrangian in order to construct kinetic energy and potential energy matrix, right? So Lagrangian, 1 over, okay, T minus V, of course, you know, 1 over 2. On purpose, I usually try to keep it outside so that I wouldn't include it in my matrices. So it's better to keep it outside of the bracket. So then, kinetic energy, 2 masses, so it will be, okay, relative to the previous system, what's the difference? There we had 3 masses, now we have 2 masses. There we had 3 springs, now we have, no, there we had 2 springs, and now we have 3 springs. So it will be m eta 1 dot squared plus m eta 2 dot squared, then minus, again, 1 over 2 I will keep outside. And another thing, I've seen in the past several times, students made this another mistake, typical mistake. They tried to include minus, which is between kinetic and potential energy, into the potential energy matrix of potential energy matrix. No, this minus is not part of the potential energy matrix, right? So T minus V, this minus stays outside. So now potential energy. So we'll have now 3 potential energies. First, K, and stretching of the spring is determined only by this coordinate, because here it's fixed. So here there is no stretching. So now it will be K and eta 1 squared. Then the middle one plus, 1 over 2. No, 1 over 2 is outside, sorry. Then this middle spring, K, and of course stretching depends on the difference between eta 2 and eta 1. So it will be eta 2 minus eta 1 squared. And this one, that spring, is stretched only by eta 2. So it will be plus K eta 2 squared, right? Okay, so now let me arrange it better. Okay, combine some terms over there. 1 over 2 m eta 1 dot squared plus m eta 2 dot squared minus 1 over 2. Now, 1 eta 1 squared appears from here, so we will get 2k eta 1 squared. Then another eta 2 appears from there, gets combined with that, 2k eta 2 squared, and then cross term minus 2k eta 1 eta 2. So now basically this, after this form of the Lagrangian, we can write down kinetic and potential energy. Again, 1 over 2 and minus are outside. So kinetic energy matrix, of course, will be reasonably trivial, m0, 0, m. Then potential energy matrix. Diagonal elements 2k, 2k. And of diagonal elements, of course, we need to split this term into two. Minus km eta 1, eta 2, and minus k eta 2, eta 1. So it will be minus k, minus k. So both real and symmetric as they should be. Right. Okay, so now, of course, we need to use Eigenvector Equation. Right.
Wouldn't that be V T, the second one?
Oh, yeah, of course. I started rushing myself so that, yeah, absolutely, absolutely. Thank you. Right. No, I'm getting more excited the closer to the end of the semester. But usually still, the final exam week, it's still so busy preparing all the exams, makeup exams, like especially physics 2, there are usually several makeup exams. All right, okay, and of course, determinant of that system must be equal to 0, so it will be determinant of omega squared t equals to 0, and of course, from here we can get all eigen frequencies. All right. So there are how many eigen frequencies? Of course, 2, because we have a system with 2 degrees of freedom. Right. Degrees of freedoms are determined by the masses, not by the number of springs, right? All right, and of course, again, we assume it's a linear system, right? So, linear system, no movements, no motions in a vertical direction. I should have mentioned that. So then frequency omega 1 equals square root of k over m. And you know what? Let me label it as omega. Just minor compulsion. I just don't want to drag this subscript, because the second frequency I will also write in terms of this omega. Again, it's not a crime, just I want. And omega 2 will be equal square root of 3k over m. Okay, so of course I can write it in terms of omega. It will be square root of 3 times omega. Square root of 3 times omega. Okay, so now these are, you know what, let me sort of frame them so it would be easier for me to spot them if I need. Okay, so now after this, we need to shove them in the Eigenvector equation, and of course, you will end up, and after normalization, I will skip all that, because I just want to get to the general solution, so that I can compare then this approach, results of this approach with the results of that tricky approach, right? But of course, I don't want to waste time getting through procedure which we already discussed. So, eigenvectors. The first one, with normalization factor, square root of 2m, and it's a 1, 1. Then a2, the second, the same normalization factor, yes, 1 over square root of 2m, and now it's a 1 minus 1, yeah. 1 minus 1. So in the first normal mode, both particles are displaced in the same direction, right, with the same amplitude. In the second mode, out of phase. Again, I don't want to draw those modes. Okay, so now general solution. Pretty much that's what I wanted to get. Now general solution. So it will be eta 1, eta 2. And which constant I use? C1? Yeah, C1. C1. In this case, C is a real constant. divided by the normalization factor, and 1, 1, and the time dependence cosine omega t plus delta 2. Omega, it's this newly introduced constant, right? Yeah. And now the second, c2 over square root of 2m, column 1 minus 1, and cosine square root of 3 omega t, square root of 3 omega t plus delta 2. So, general solution. Okay, I need to frame it with red because, as I told you, I want to compare this result with the result which I'm going to get using not conventional approach. Okay, so now I will put the second bullet, and now the trick method. Right. Or approach, whatever. All right. Okay. So now, let me now rewrite Lagrangian, since now I'm not going to write this potential energy matrix, kinetic energy matrix, right? So let me write Lagrangian in normal way, when 1 over 2's are included, minuses are included, just normal Lagrangian in the most convenient form, because this was most convenient in order to write matrices. Okay, so now let me rewrite basically Lagrangian. So it will be m over 2 eta 1 squared plus m over 2 eta 2 dot squared. And now it will be minus k eta 1 squared, then minus k eta 2 squared, and then will be plus k eta 1 eta 2. Okay, so this is the simplest form from the mathematical point of view. Right. Okay, and then typical Lagrange equation, right? So Lagrange equation, which is d over dt out of partial derivative of L with respect to eta 1 dot equals to partial derivative of L with respect to eta 1. Okay, so now let's write down the equation, which is trivial. So it will be m eta 1 double dot, m eta 1 double dot on this side. On that side, it will be more productive. Eta 1 is here and there. So it will be minus 2k eta 1, minus 2k eta 1. And from here, it will be plus k eta 2. Okay, the first equation. And the second equation, of course, similar for the second coordinate. And so, of course, if you apply it, it will be m eta 2 double dot equals, now the right hand side, it will be you know what, let me write first. Did I get it right? Let me compare. Okay. I just, next step, I will divide it by omega. Okay, but that will be the next one. All right, so it will be minus 2k eta 2 and plus k eta 1. Okay, so now let me divide everything by m in order to get rid of any factors in front of the second derivatives, right? In order to make differential equations the most convenient. So as a result, eta 1 double dot equals to, probably first I will write, actually I moved to that side. Okay, why not? So plus. So this will be with minus, it will be 2 k over m, it's a 2 omega squared eta 1, so plus 2 omega squared eta 1, right? Yeah. And so this will go with minus, so it will be minus omega squared eta 2. Minus omega squared eta 2 equals to 0. Okay, so looks like this is the most convenient form of this differential equation. And very similar, of course, will be for the second one. Eta 2 double dot. Now, I will write term with eta 1 first, right? Or not? Okay, why not? In my notes, first eta 2. All right, so it will be plus 2 omega squared eta 2, and then minus omega squared eta 1 equals to 0. Okay, so these are differential equations. These are differential equations. And now, at this point, they're coupled. Here we have eta 2 among eta 1s, and here we have eta 1 among eta 2, so coupled differential equation, right? But it's not horrible system, not horribly coupled. So, and it means that if we stare for this system of equations for some time, you will start noticing that if we massage these equations, we will be able to get solutions easier. In which way? For example, okay, let me label this is equation 1, and this is equation 2. Look, if I, for example, add 1 and 2, so what if I add equation 1 and equation 2? Right? So we will get here eta 1 plus eta 2 double dot. Then here we have eta 1 and here eta 1. If we add them, here we have plus 2, here minus 1, we will get omega squared, eta 1. And this also positive and negative, if we add them, we will get just omega squared eta 2 with plus. So if omega squared can be factored out, we will get again omega squared eta 1 plus plus eta 2. It looks like we're getting what we would like to have, plus eta 2 double dot, and then plus omega squared eta 1 plus eta 2 equals to 0. Magic, right? Of course, this equation can be easily solved, of course, in terms of eta 1 plus eta 2. So now, if we introduce new coordinate as eta 1 plus eta 2 and give it a cool name, normal coordinate, we're getting normal coordinate. And it will oscillate only with the frequency of omega. All right? Okay, all right, so now if we denote psi as, okay, psi 1 as eta 1 plus eta 2, okay, I can put 3 lines basically by definition. That's how I want to define it. So now, of course, differential equation is trivial and decoupled. It depends only on newly introduced coordinate psi 1. So psi 1 double dot plus omega squared psi 1 equals to 0. Solution of this is piece of cake. So because it's a single oscillator, right? Differential equation is not coupled, right? So of course we can write, so psi 1 equals, which constant I use? All right. Okay, A1. You know what? I doubt that I will have enough space. Let me move to the next line. So as a result, psi 1 equals to A1 cosine omega t plus delta 1, right? Omega, it's that omega, which is that, right? Probably I introduced this omega, but I didn't define. Okay, it's not a good idea. It's not a good idea. So omega equals square root of k over m. Since we use this definition so many times, so sometimes you just assume that, of course, everyone knows that. And of course, everyone knows. So which is our omega 1, right? Okay, so that's the first solution. Now, you know what? This I need to frame. Now, let's keep staring because we, at the end of the day, we will have to get eta 1 and eta 2. Now we solve it in terms of some crazy psi1. Again, at the end of the day, we want to see actual displacements of particles from the equilibrium. We want to get eta 1 and eta 2. So we need to get the second equation somehow out of this, right? So now, what if we subtract 2 from 1? Oh, wrong color. All right, so what if we now subtract equation number 2 from equation number 1? And so now again, let's start staring eta 1 minus eta 2. Right, so it will be eta 1 minus eta 2. Again, double dot. And what? If we subtract, so it we'll have here 2 eta 1s. Here, minus and minus, we will get another plus. So we'll get 2 plus 1, 3 omega squared eta 1. Then, if we subtract this from that, it will be minus that minus this. So again, it will be now minus 3 omega squared eta 2. So we can factor out 3 omega squared, and we will move it to that side. So it will be, they're all on that side, so it's fine. So plus 3 omega squared eta 1 minus eta 2 equals to 0. Again, we can easily solve this equation in terms of eta 1 minus eta 2. So let's introduce the second normal coordinate. And you see it oscillates, this new coordinate oscillates with the second frequency of the second normal mode. Right. So now, again, let's denote psi2 as eta 1 minus eta 2. And then, of course, differential equation is trivial psi2 double dot plus 3 omega squared psi2 equals to 0. Piece of cake, right? So, of course, solution can be easily written, right? Psi2 equals, okay, now constant a2, let's say, a cosine square root of 3 omega t plus delta 2. Okay, so now we have two solutions in terms of psi1 and psi2, right? And again, oscillates only with the frequency of the second mode, right? With frequency omega 2. Psi1 with the frequency omega 1. So yeah, these are normal coordinates. So psi1 and psi2 are normal coordinates. You see, we managed to get them without getting through this tedious fail-proof procedure. But of course, it can be done only if this system of differential equations is reasonably nice. So you can, if you stare for some time, you can see what you can do in order to basically introduce new variables in terms of which differential equations can be decoupled, right? Okay, so now we have solutions in terms of psi1 and psi2, but of course, again, at the end of the day, we need to go back to eta 1 and eta 2. And of course, that can be easily done. So let me combine these definitions, okay, of these normal coordinates. All right, so let me combine them. Psi1 equals eta 1 plus eta 2. Psi2 equals eta 1 minus eta 2. And if we want to inverse, so basically these are transformation equations, right? Time-independent transformation equations. Now, if we want to go back, of course, it will be, you can easily do it. It will be, I think, psi1 plus psi2, yeah, divided by 2. Psi1 plus psi2 divided by 2. That's how you can reconstruct eta 1, and you can reconstruct eta 2 as the difference psi1 minus psi2, yeah, right, divided by 2. Right. Okay, so now we can write general solutions of the first particle. Now, yeah, of the first particle and the second particle. Because again, what psi1 and psi2 determines, it's something from the physical point of view not very interesting. From mathematical, yeah, it's nice. It's simplified solutions. But that's where it's better to see physical meaning. All right, so now as a result, eta1 will be equal. So psi1 plus psi2. So okay, I need to frame this psi1 and psi2 because now I started searching with my eyes where those solutions are. This and this, right? Okay. So it will be this plus this divided by 2. So it will be a1 divided by 2 times this cosine. Hold it. Yeah, that's it. Omega t plus delta 1 and plus a2, right? Yeah, a2 divided by 2. Cosine of square root of 3 omega t plus delta 2. Okay, so now we can rename constants of integrations. Instead of a1 and a1 and a2, we can introduce, for example, b1 and b2. All right, just to dump that factor of 2. And so for eta1, of course it will be, so now psi1 minus psi2, so it will be this, basically this minus that. So it will be a1 over 2 cosine omega t plus delta 1 and minus a2 over 2 times cosine of square root of 3 omega t plus delta 2. And again, the same constants of integration, which, so we can again rename them as beta 2 and beta 1 and beta 2. And so now we can write general solution. Okay, these are general solutions of particles 1 and 2. Now, if you want to write general solution of the whole system, combine these two equations, right? Write them in a matrix form, okay, in the column form. Right. So now we can write, so general solution eta1, eta2 equals beta 1, 1, 1, beta 1, 1, 1 column, and times cosine omega t plus delta 1. So it's exactly the same, but eigenvectors are not normalized. This eigenvector is not normalized. Okay, bigger deal, you can easily normalize it if you want now, right? But you see, the first term exactly the same, but here they are normalized, they're not. And so the last plus beta, b2, not beta, 1 minus 1, and time dependence with the frequency of the second normal mode. Cosine square root of 3 omega 2 t plus delta 2. The same, but not normalized. Okay, so let me write, so the same, but not normalized, but not normalized. Okay, you understand, I'm talking about eigenvectors, not normalized, right? Not normalized. Right. Which is nice, but not completely necessary, right? And you know what? We still have 7 minutes. If you, for example, let's say, okay, so that's what basically I mean by the trick. When you write differential equations, just stare at them and see what you can do with those differential equations in order to get equations like this, right, which can be solved immediately. Basically, how can you decouple them? Okay, then let's go back to our fail-proof approach. So, okay, let's assume that you got this general solution of the whole system, right? And now next step, let's say you want to get a normal coordinates. Of course, the procedure is known, right? So you need to, again, construct the model matrix and then multiply what A transposed T eta, and that will be Xi, right? Something like this. But what if you don't want to go through that mass multiplying matrices, right? You can reasonably easier sometimes, again, if the system is reasonably nice, by just looking at the differential, at the general solution, you should be able to get structure of normal coordinates. What do I mean by that? Look, first normal coordinate, it must, okay, must, it should, okay, oh, must, okay, whatever, oscillate with the frequency, with the first frequency, with this frequency, right? So it means that we need to dump this, for example, term with this frequency. So how can it be done? Again, we need to construct a linear combination. Look, what if I take one part of eta 1, so here we have 1, and then one part of eta 2, and just add them. We'll have here amplitude 1, amplitude minus 1, because, okay, factors in front and that factor, they're exactly the same for all of our coordinates. So if you take one part eta 1 plus eta 2, so 1 minus 1 gives you 0, and it means that that new coordinate, which is eta 1 plus eta 2, is not going to oscillate with this frequency. Right? So that's how you can see immediately that first normal coordinate is normal coordinate xi. So xi 1 will be eta 1 plus eta 2, and of course this linear combination is not going to kill this term, so it will oscillate with frequency omega. Now let's say how we can construct the second normal mode, normal coordinate. So now we want to keep this, and we want to dump oscillations with this frequency. So what should we do? We need to take one part of eta 1, one part of eta 2, and now subtract them, so that 1 minus 1 and the frequency oscillations with this frequency will disappear. So you will get immediately psi 2 equals to eta 1 minus eta 2, right? So if you don't want to get through this multiplication of columns and matrices, yeah, you can just, by looking at that, you should be able to get the linear combinations of etas, which can give you normal coordinates. Okay, another example like that, in order to sort of finish. What if what can be erased? Probably I will erase this part. Yeah. The end. Okay, so I will probably put a new bullet. All right. So what if we have, for example, this situation? Example. Again, pretty much now, what's the idea? Again, if you have general solution, how you can construct normal coordinates without getting through this procedure. Okay, so let's assume that we have this general solution. Okay, I grab my notes, so it will be, let's say, eta 1, eta 2, and let's say we have constant C1, then let's say 3, 2 cosine omega 1 t plus delta 1. I just made it up, basically, right? And let's say plus C2 and 1 minus 5 cosine omega 2t plus delta 2. Let's say we have this general solution. And sort of I'm lazy to construct the model matrix, transpose, kinetic energy, multiply by 8. Okay, so I just want, by staring at this solution, I want to write normal coordinates. So psi 1 and psi 2. So in psi 1, I want psi 1 to oscillate only with this frequency omega 1. So it means that there shouldn't be a contribution from that. So how can that be done? So I need to take, for example, 5 parts of eta 1. So over here upstairs I will have 5. And 1 part of eta 2 and add them. So I will have 5 minus 5, amplitude 0, and my new coordinate is not going to oscillate with the frequency omega 2. So you see, I can construct it like this. So it's a 5 part of eta 1, and then subtract 1 part of eta 2. And as a result, my newly constructed coordinate, normal coordinate xi1 will oscillate with the frequency omega 1. Right. So normal coordinates associated with the first normal mode. Then xi2. So now I want to keep this. I want xi2, my xi2 oscillate with the frequency omega 2, so I need to dump this. So how can that be done? I need to take 2 parts of eta 1 and subtract 3 parts of eta 2. So it will be 2 eta 1 minus 3 eta 2. And that will give me oscillations only with frequency omega 2. Right. But again, it can be done only if the system is reasonably nice, right? If you have more particles, of course, it's more difficult to see. But of course, the
wouldn't you add for theta 1 because it's a negative 5?
The first one. Yeah. Okay, I need to look at my notes often. Yes, of course. Yeah, add. And here, yes, subtract 2, 3. Yeah, this is correct. Right. Okay, so there are some tricks, but again, if you want to be safe, fail-proof approach.